have a different experiment. Roll the dice. Roll the dice. So what is the sample space here? What are the possible outcomes?
1 to 6.
Exactly. But we could have also, we can still roll a die and ask a different question. So the experiment is not what is the number that comes, but whether it's even or odd. So in that case, we would have two possible outcomes, or odd or even, right? So you see, the experiment is not only flip a coin or roll a die, it's the question. So what is the thing, what are the possible outcomes we consider? And from the same action, we may have different outcomes, right? Different sets of outcomes, different sample spaces. And okay, now what is the sample space if if I flip two coins?
It may be head, 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 tail, tail, head, and tail, tail.
Exactly, right? So these are the possible outcomes if we flip two coins. So what if we flip a coin and roll the dice?
It can be heads with either one of the 1 to 6 outcomes, or tails with 1 to 6 outcomes.
So you mean this, right?
Yeah.
Yeah, I don't want to write all of them. And here's the same with tails. So what is the cardinality of S, of the sample space?
12.
And why is that?
Because every sample is unique. Every element in sample is unique.
Well, yes. But is there another way to, so what is 12? Okay, what was the flip a coin cardinality?
2.
For 2, yeah.
And what was for roll a dice?
6.
So what is 12?
It's 2 by 6.
2 times 6, right? So in order to compute the probabilities, it is very, very important to figure out the sample space correctly and to be able to compute the cardinality of the sample space, okay? To know how many outcomes, possible outcomes we have. So now let's go to the next important definition. People still join 15 minutes after we started. So an event is a subset of the sample space. Okay? That's a very simple definition, but also important. Okay. Now, for example, in our standard, so let's say our experiment is to flip 2 coins. And we said that in that case, the sample space is heads, heads, tails, tails. So here's an event that we have at least one tail. Okay, so that's a subset of the sample space, so it is an event. Any subset is an event. Actually, also the empty subset is an event. It's the empty event, which can never happen. And also the whole space is an event, which always happens, right? Because if you do an experiment, one of these things must happen, must be observed. Okay? Let me remind you that in general, because this will be important, if we have a set, so if we will denote by prime the complement of phi, which is all the elements in the sample space that do not belong in E. Okay? This is the complement. Question. If we have 2 events, A and B, what about A intersection B? Is this also an event?
Yeah, it might be.
It might.
Like if they don't have an intersection, well, if we consider and the empty set as an event, it will surely be.
So this is also an event because this is always a subset of, so if A and B are events, it means that they are subset of S, right? So then their intersection is also a subset of S. So this is also an event. It is an event consisting of all the outcomes that are common to both events. For example, if here we had E2 saying that the first outcome is a tail, then E1 intersection E2 is actually the same as E2, right? But if we had another one saying that the second outcome is a head, then we would have this and that, and the intersection of E1 and E3 would be only this, which is still a subset, so it's an event. Do we all follow?
Yeah.
Yes, sir. But I have a question. If it is a empty set, it's still an event. Am I true now?
If it is empty,
Yes.
yes, the empty set is also an event.
All right.
It's a very boring event that never happens, but yeah. So it is important that since we defined an event as a subset of the sample space, the empty set is also a subset, and it's always a subset, right? So, and we will see later why it is, we really want the empty set and S to be events. So now, 2 events, A and B, they're called mutually exclusive or disjoint. if the intersection is the empty event, is empty. Okay, so if they have no elements in common, then they're called mutually exclusive. I mean, why do we use this terminology? Why is it mutually exclusive? Because we have two events, and after we perform the experiment, we know that the observation cannot be in both of them. It's either in one or the other, or none, maybe, but it cannot be in both of them at the same time. The outcome we will observe cannot be in both events. This is why they're mutually exclusive. If one happens, then the other cannot. We're okay?
I didn't really understand it. Can you repeat it?
So the point is that if we have two events whose intersection is empty, it means that they do not have any element in common. It means that none of the outcomes, the sample points they contain, they have it in common. But after we perform the experiment, only one outcome is observed, right?
Yes.
If you flip a coin, it's either heads or tails, right?
Yes.
So since there is only one outcome observed, this outcome cannot be in both A and B, because otherwise it would be in their intersection.
Yes.
So if A happens, then B cannot happen. If B happens, then A cannot happen. And this is why we call them mutually exclusive. One excludes the other
Okay, I understand.
from happening. It's possible that none of the two will happen, but if one happens, then the other cannot. Do we agree?
Yes, thank you.
Okay. Now, we saw about intersection. The union of two events well, it's A union B, right? Is it an event?
Yes, it's all of the events of both A and B.
Yeah, it's exactly, it's an event that happens whenever either A or B happens. So events are subsets, right? So you know how to deal with subsets. You can take unions and intersections. We don't need to spend too much time thinking about that, right? So since they are sets, subsets of S, everything we know about sets holds. We can also use Venn diagrams, obviously, which sometimes we do. It's useful. Are there questions until here? These are some very, very basic and important definitions that we have to understand very, very well. So what is the sample space? What is an event? And what is an outcome? Is it clear to everyone?
Yes.
Okay, great. Then let's start counting the size of sample spaces, okay? Because that's a very, very important thing. By the way, okay, let me ask you now. So we flip a coin. What is the probability of having heads? Someone?
50%.
Sorry?
1/2.
1/2, right? Why?
Since there is a two possible outcome and there is no difference between them occurring, so that must be it.
Okay. So you say that actually here, so what you say is here I have the sample space, right? The size of the sample space, and here something else, the size of some event, right?
Yes, sir.
So this is what you described, and this is really the definition we will see later. But as you see, we really have to count the cardinalities of these sets. So we will spend some time thinking on how we count these sample points. Okay? Now, this is a very simple thing we saw before, right? So if an operation, something we do, flipping a coin or whatever, if an operation can be performed in n ways, and then a second operation can be performed in m ways, then together they can be performed in n times m ways, right? So this is exactly what we saw with 2 times 6 before, which was 12, right? Also, for example, if you flip, if you roll 2 dice, how many outcomes? What is the sample space size?
36.
So I will ask, so don't, instead of answering directly, you should raise your hands and I will start asking questions. So Ali Bahar.
Yes.
What is the size of the sample space if we roll 2 dice? Sorry?
So 36.
Why is 36?
For one dice, there is 6 possibility.
Yes.
From 1 to 6. Multiply 6 by 6, 36.
Okay, great. So just by using the rule above, we get 36. Thanks. So I mean, in general, now if we have more than 2, we just multiply more things. Right? So we had if we roll 2 dice and then flip a coin and then roll another dice, etc., we will just multiply 6 times 6 times 2 times 6, right? Okay. Questions? No questions. So what is a permutation? It is an arrangement in specific sequence of a set of objects. Okay? So, I don't know, you have balls of different colors, and then you have different ways of arranging them, like red, green, blue, blue, red, green, etc. Okay? Is it clear what a permutation is?
Yes, sir.
So now the question is, how many permutations do we have? Let's say you have a set of n elements. How many permutations does it have? Bouze. Bura. Gem. A leaf.
N factorial divided by n minus r factorial.
I knew that a leaf would work because it's 5 of you, so at least one of you would answer, right? So, yes, it is n factorial. Thank you. So, why is it n factorial? Same a leaf or another leaf?
Sir, it's me. She's me.
Ah, okay.
I didn't understand. Sorry.
So why is it n factorial?
Because of permutation is arrangement system. So if we have a set of numbers,
Yes.
we want to arrange these numbers. We use general factorial.
But why? I mean, the point here is we want to think how to compute this because we may have some small variation. So we'll have to be able to think of this variation afterwards, right? So what is the idea? Why is it n factorial?
Can I answer? When we calculate the value of permutation, we should regard the order of all arrangements. So it's equal to n factorial.
Yes, but why?
Because of regarding orders, maybe.
Sir, may I answer?
Okay.
since there are n elements in our set, there will be n place for every element. So if we calculate, that will be n factorial.
Okay, but what do we calculate? You have n positions for the n elements. Okay.
Sir, can I say something?
Of course.
If I have n elements, we use we said that we find the possibility with multiplication. In step 1, we have n chance, and second step we have n-1 chance. This becomes we have a factorial system. I didn't explain
Yes,
that.
so combining the answers of Bilal and yourself. So we have n positions, right? Here. And we have n elements. So when the first element comes, we have n choices on where to put it. I can put it here, for example, okay? Or anywhere. After I put it somewhere, see, this is a repeated operation I'm doing. For the second object, I don't have any more n choices, but I have n-1 choices. For the third object, I have n-2 choices. And the last object, there's only one position possible, so that's n factorial, right? So this is just the multiplication rule from before. We just multiply the ways of doing things, of doing an operation, and we have n operations, okay? Now, what if I don't want to have the permutation of all objects, but I want to have permutations of R out of n objects. Okay? So instead of having, I don't want to have all n objects in my permutation, but I choose only R of them, and I want all the permutations of these things. Ideas?
Can I answer, sir?
Yes.
Actually, first we take n times. Sorry. We multiply n times n-1 factorial because we use r elements out of n objects. There are just r objects that we can use.
But I don't see R in what you said. You said n times n-1 factorial.
Actually, n times r factorial, maybe it can be 2.
These are different things.
Yeah, no, I have just realized that what I think and said is different. So
Can I try, sir?
Yes.
So if we have R out of n elements, so if we have R is equal to n, it's directly n factorial. But if we have R elements, so for the first element, it's going to be n places. For the second element, it's going to be n-1 until n minus R. So it's n so it's n minus. So it's n factorial minus n minus r factorial, or Yeah, I don't know. I didn't do the computation correctly.
So do we reach to n minus r or plus 1, right? No,
Yeah.
because these are r.
Yes.
So this is the number of permutations. That's correct. It's n factorial divided by n minus r factorial. Okay.
Okay.
Sir, I couldn't get the formula.
So for the first object, we have r positions. And we have n objects, right?
Yes.
I want to fill, in how many ways can I fill the first position? In n. I can choose any of the objects. In how many ways can I fill the second position? Well, n minus 1, because I used one already, right?
Yes.
Continue like that, and you will have to do this r times, and you will see that, yeah, so it is n minus r plus 1 ways for the last one. If r is equal to n, this is 1, which was the case here, right? Here we can start, for the first position, we have n choices. For the second, we have n minus 1. This is the opposite way of how we thought. You can either think of how you place objects in boxes or how you fill in the boxes, right? So if you think of how you fill in the boxes, you have n choices for the first one, n minus 1 for the second, n minus 2 for the third, etc. And this way, it's easier to think here. You have n choices for the first, n minus 1 for the second, n minus 2 for the third. And for the rth, you have n minus 1, n minus r plus 1. Right? And if you do this, this is n factorial divided by n minus 1 r factorial, because that's what remains here, right? So if you continue, this would be n minus r times n minus r minus 1. So this is n minus r factorial. Is it better?
Yes, sir.
Okay. Now, here's the question. Let's say we have, so we want permutations of n objects that are of different kinds. And one of them of the first kind, actually, let me write it properly. And I of these objects are of the ith kind, and there are k kinds. So we have groups of objects, right? And you want to take the permutations such that n1 are from the first group, n2 are from the second group, etc. Okay? This is a very common thing to do, by the way.
So alternating objects?
No, so think of it this way. So you have you separate your you have your sample space, you have your objects anyway, and you say that you can call them red, green, blue, right? So you have balls with numbers, but also colors. And you say, I want to permutations where I have only 2 red, 3 blue, and 1 green. Since I can do this here, let me actually, so we have, so let's say this is our set of objects, right? And from this set, I want to, I want to have permutations where I have 2 red, so n1 is 2, 1 green, which means n2 is 1, and let's say 1 blue, n3 is 1. Okay. How many such permutations do I have? You have 2 minutes. Think about it.
Sir, can I answer?
Yeah, wait. So let people think more.
Okay.
So I don't want. So I don't know if 48 is correct, but I want you to also give me the formula how you compute it. 1 more minute. Okay, raise hands. I think Jan was asking before.
Okay, I want to explain it step by step.
Okay.
For red ones, we can say that 3 factorial over 1 because of 3 minus 2 is equal to 1 and it's equal to 1 factorial according to our calculation. For green ones, 4 factorial over 3 factorial because of 4 minus 1 is equal to 3 factorial. And for blue ones, 2 factorial over 1 factorial, because of 1 over 2 minus 1 is equal to 1 factorial. So it should be the result, I think.
Do we agree?
I don't agree.
I agree.
I don't agree because this is the possibilities of our choices, but we didn't order them actually. So we need to order them, and we need to multiply it with sum of n's from 1 to k.
So you say 4 factorial.
Yes, in this case, 4 factorial.
Okay. So now do we all agree?
Yes.
So in general, if we had n objects, ni kinds, ni for every kind of k kinds, what you say, this is n factorial times, what was 3? So it's ni factorial, the product, right? And what was the denominator? Ni okay. So is this example an example of this problem?
No, it's not, I guess.
Why?
Because in our example, we had a total of 9 balls, but we have only 4 places to place them. In the example, in the NI example, we didn't have any like difference in the number of items.
So here actually, this ni is not that ni, right? So this is a very, very different problem. So, and I think you're correct. So for the first, so we have, for the red ones, yeah, so this is the correct answer. I need an extra symbol here because, so let's say this is R, this is green, and this is, no, that's a bad choice. So let's say the cardinality of the set. So here this would be Ci minus Ni, right? Factorial. And then indeed we have to permute by n, which is the number of positions. So this is the correct answer for that problem, which is not what I wanted. I'm sorry. I constructed the wrong example for the formula I wanted to give. It is correct. I'm wrong. But that's exactly why we do these exercises, in order to be able to construct, to think how to come up with these formulas. I mean, you don't have to remember, you have to know them because, I mean, they're simple and it makes sense, but you have to be able to come up with them in your own. So the problem here was this thing. Actually, what we have is that N1 is 3. N2 is 4, and N3 is 2, right? So it's the number of elements from each group. And now I want permutations of n objects from these kinds. So until now, essentially, we had distinguishable objects, right? Now, what I'm saying is I don't care about the numbers itself. So the objects are not all distinguishable. I have still 9 objects, okay? But I cannot distinguish between 2 red balls. They are the same. All 4 green balls are indistinguishable. So what I want is the number of permutations that I can distinguish between, where I have 9 objects, but 3 of them are the same, 4 of them are the same. I have groups of 3, 4, and 2 objects. What do I do now?
Can I answer?
Yes.
I think the result is 3 factorial over 3 multiply 4 factorial over 4 multiply 2 factorial over 2, because they are the same, and we need to consider that when we permutate them, we cannot distinguish between them.
Okay, but how do you? Okay, let's take one of these. So one of these permutations is this. Right? Now, let's for a moment assume that these were numbered. And this was 2, 1, 3. And the rest the same. So these 2 permutations in our setting are the same because we cannot distinguish.
Yes.
But if we could distinguish, how many permutations do we would have? If all of the balls were distinguishable, how many permutations we would have?
9 factorial.
9 factorial, right?
Right.
Now, there is also another one here that is, so I permuted the red ones and I get the same thing, right? I can also permute the green ones and still get the same one. I can also permute the blue ones and get the same one. So I want all these different permutations, which if we only consider colors, they're the same, but if we consider numbers are different, I want them to be all the same, right? So I want to divide this number. In n factorial, all these are different. But I want to make them, not to count them again, right? So how many, shall we do a much smaller example for a moment? So let's deviate a bit from our example and make a small example. So I have one red and two blue. Okay, so what are all the permutations I can have here? So I can also have this, because so this is 1, 2, 2, 1, 1, 1. Well, I mean, I don't need to write the red one, right? Then I can also have uh, 1, 2, 2, 1, and I can also have this, right? So in total I have 6, but I want them to actually be 3, right? Because these are essentially 3 different permutations if we forget the numbers, right? So what I want is, what is what I want here? What was 6?
N factorial.
6 is 3 factorial, because I have 3 balls, right?
Yeah.
And what do I divide with?
3
1
minus
factorial
2
and
factorial.
multiplied by 2 factorial.
And why is this?
Because we don't want the permutations of a color in themselves.
Exactly. So here I will take all the permutations of red, right? So this is n1 factorial. Then I can also permute all green between them, and k factorial. Okay. So this is the number of permutations where we have objects, n1 objects, ni objects of the I kind. If we cannot distinguish between objects within the same kind. Is it clear to everyone?
Yes.
Sir, can I ask a question?
Yes.
The below formula is for the bottom one, right? They have numbers. We can distinguish them.
No. So the point is, if we can distinguish them, then it is 6. It's 3 factorial. But if I forget about distinguishing them, then the different ones I have are these 3. Right? This is the same as that. These 2 are the same if we forget the numbers. So I want 3. I want to not to take into account when I permute the blue things in between. And this is why I divide by 2 factorial, because this is the number of permutations of the blue things only. Right?
Okay, teacher.
So here, this will be 3 factorial, 4 factorial, 2 factorial. So in total here, let's see if this was correct. So this is, what is it? It is 9 factorial divided by 3 factorial, 4 factorial, 2 factorial. How much is this? Yeah, it doesn't look like the same, right? So this is 98765, right? And then 3 factorial 2 Is it? So this is 3 times 2.
I got 1,260.
That's a nice number. But I don't know if is this the same with that? I don't think so.
No, it's not.
No. It's full.
Okay. So, yeah. Questions? Okay, now let's forget about order. And the question is, how to choose R objects out of N. I have N objects and I want to pick R of them. So these are combinations. I don't care about the order. How many combinations do I have?
Can I answer, sir?
Yes.
N factorial multiply n eksi n minus r factorial over r factorial.
This is what you mean?
Sorry?
This is what you mean?
I think it is a combination of n of r. But should we do n of r or r of n?
Well, N choose R.
Okay.
We choose R out of N. This is the notation we use. So this means we choose N out of, or R out of N objects, okay? But is this correct? So how do you think about it? How did you come up with this?
Because we should do a combination. So how can I say? Actually, I know the combination and I write this formula, but I cannot explain now.
Okay.
Maybe I should think 1 minute.
Can I answer?
Yes.
Can we say that n factorial over n minus r factorial multiplication with r factorial?
Why?
Is equal to because we choose r out of n, and it's also equal to permutation with n and r over r factorial, as far as I remember.
Well, it's not about remembering, it's about thinking. So how do we think about it?
Can I try to answer?
Yes.
So if we have R objects, for the if it's n objects, we have n factorial ways of choosing the objects, of combining them. But if we have the first object, we have n objects to choose from. But for the second object, we have n minus 1 to choose from. And this goes until n minus r. So that's n minus r factorial. But overall, it's we have n factorial, so it's n factorial over n minus r factorial.
You confused me a bit in the end. So,
like if we had n objects, it would be n factorial. But if we have r objects, it's n minus r factorial.
Why is it n minus r and not r factorial?
Because if we for the first one we have n ways of choosing, but for the second one it's n minus 1 ways for choosing.
So the point is that here we choose the objects and we don't care about the order of these objects.
Yes.
We don't care what we picked first and second.
Oh, okay.
So one way to see this is that we take all permutations, which are n factorial, right? But then we don't care about how things are permuted within the group that we chose. These are R factorial. Between these R objects that we chose, we don't care, right? And we also don't care about how they are in the rest, how they're permuted. So in general, if we want to move from something that is from ordered to unordered, we don't care about order, then we divide with cardinality factorial, because this would give you how many permutations you have. So if you want to forget that, you just divide with this number, right? But that's not correct. This is correct. This is a number of combinations. Okay? Questions? Okay.
Can you explain formula again, please?
So let's see. I have n objects. How many permutations do they have? N factorial, right? Now I have two types of objects, the ones I chose and the ones I didn't choose.
Yes.
Within each of these groups, these are two kinds of objects, right? Remember, it's the same as before. Within these kinds of objects, I don't care about the order. What is the cardinality of the first kind? R. These are the kinds I chose. What is the cardinality of the other kind? Well, it's the rest.
Okay, so thank you.
So you can think of this as different kinds. One is the kind you chose, and the other is the kind you didn't choose.
Thanks, sir.
But we do care about, yeah, so we have these two groups essentially, yeah. Okay, so I want you to do also the exercises from the first, so this is the 2.1 and 2.2 from the book. And I will not continue now, but you should do exercises, okay? I mean, for yourself, just to get used to counting stuff properly. This will help you. And then, okay, let me say something here. Teaching online goes much faster than teaching in the classroom. But it makes no sense to give you all the material at once. I could finish the lectures, the topic in 4 weeks, but you would understand nothing. It doesn't make sense. This is not a pedagogical way to go. So we are in this special situation with the pandemic, and we have to adapt into different. We have to adapt our methods. Okay, so probably we will not do 3 hours per week, One reason is because there is less interaction. And as you probably understand, I want to have interaction during teaching. So you have to participate, but I will try to go slowly anyway in order to, we have time to cover the material. You can read beforehand. I usually say not to do this, but we have to discuss. So I want you to discuss in the classroom, okay? Okay, are there questions about everything we said today?
No, sir.
Okay, then next week we will go for actually probabilities of events, okay?
Okay, sir. Thank you.
See you.
Sir, I have a question, but not about
Yes, yes.
today. So you said that we need to choose a topic about our presentations that we'll do. Did you? I mean, I assumed that we were going to talk about this today, but
But
I
only
think
one student sent me an idea for a project.
yeah.
Nobody
So
ideas.
can we send an email today too? Maybe.
Yes, you can.
Okay. So do you want us to pick a chapter or pick a subchapter, subsection?
No, it could be whatever you want. In any way you prefer it. So
Okay.
yeah.
And if you don't choose, then you're gonna choose for us.
Yes.
Okay. Thanks.
Welcome. Have a good day. See you.